most of his week here to Bogazici. I think no less than 6 talks, including this, and 2 to Humanities 102, and others to the Physics Department and Biology Department. Dr. Lineweaver is the coordinator of the Australian National University's Planetary Science Institute. He holds a joint appointment as Associate Professor in the Research School of Astronomy and Astrophysics, and in the Research School of Earth Sciences. He has numerous degrees, and I won't be able to keep them all straight, but an undergraduate degree in history, a master's degree in English, an undergraduate degree in physics from Germany, and a doctorate in astrophysics from UC Berkeley, 1994. He tells me that he has lived in, studied in, or visited some 70 countries. His research areas include cosmology, exoplanetology, and astrobiology. He's also played semi-professional football in Germany. And he has some 50-some articles in scientific journals, numerous book chapters. I'll read you some of the titles, perhaps because I don't understand them, but they are captivating titles all the same, and may, in fact, be related to today's lecture. Signatures of a Shadow Biosphere, the Galactic Habitable Zone and the Age Distribution of Complex Life in the Milky Way, Cosmobiology, Our Place in the Universe, and one that I did understand and actually read online. Does the universe contain an infinite number of Kevin Rudd's? So here today on the subject, on the question, are we alone? Which if you'll permit me to say as a teacher, my sort of quotidian answer is, if only I were. But I don't really mean that, of course. Dr. Lineweaver.
If you have any questions about anything I say in this talk, you can write, there's my name, and you can Google my name, and you can find out publications and find out more details about some of the things I will say. Thank you, I'm glad to be here, and I'll be talking about a question, are we alone? I'm hoping that this question is something that you've asked yourselves before. I know this is a big question, it's a hard to answer question. I'm not going to be able to say definitely yes or no, but what I will be talking about is some of the evidence that we have today. It's indirect, it's suggestive, but I still think it's powerful and should not be ignored. So I'm not going to promise you a definitive answer, but I'm going to promise you the latest information we have that can suggest what the answer would be. Now, about 10 years ago, I started. There was this television show, what's the name of this television show? The X-Files. And it was very popular. And the university, like many universities, wanted to have a lot of students in their classes. So there was like a competition between the academics. Who can invent the most popular class so the most students will sign up so that particular department would get the most money from the university? So this particular show was so popular, we said, well, the truth is out there. We are astrophysicists. We're cosmologists. We know much, much more about the truths that are out there than the Hollywood producers of this show. So why don't we start a lecture and call it, Are We Alone? The Search for Life Elsewhere in the University. And you can see that's me with my soccer ball. And so a lot of people signed up, and in 2,000 or 3,000 students sign up for this course, and the department got lots of money. And so I'm going to give you a brief one-lecture version of this course. Now, at the beginning of the course, one thing I always did was take a survey. Are we alone? There are three possibilities: yes, no, and huh. Now, I've done this probably in many, many places, and I wanted to see if Turkey is any different from the rest of the world. And so, please raise your hand. Are we alone? I want you to raise your hand. Yes, we are alone. Who thinks yes, we are alone? Please raise your hand. Okay, we have about 100 people here. We have about 5 that say yes, we are alone. No, we are not alone. Okay, the vast majority, maybe 90, and how about huh? Whoa, we have a lot of huhs here. Well, that's a very sophisticated audience. So here is the results from my course. Yes, 10%, no, 80%, and huh, 10%. Now, it's interesting, here it was yes, 5%, no, about 80%, and huh, 15%. So I know I'm talking to a sophisticated audience, because after my lecture, after this course, we did the survey again. And here were the results. And I'm very proud of this. And I can see that I'm preaching to the choir here, because you already are there. So I will try to get the 15% of you up to about 20% by the end of the lecture. Now you may think that's ridiculous, but I think it's sometimes when you're learning, you have to unlearn a lot of the things you think you know, and maybe that'll happen today. Now, as I was preparing my first lecture for this class, I said, what am I going to talk about? This is do we have a subject to talk about? I'm not going to be talking about stars, I'm going to be talking about life forms elsewhere. So I was thinking, oh gosh, what am I going to say? And it happened to be the first week at the school, and during the first week there are clubs out. There are a skiing club and the caving club and the French club and the Korean Buddhist club, and then there's the Japanese Taekwondo. Anyway, there are hundreds of groups that are recruiting the new students to join their clubs. One of these clubs is the University of New South Wales SPOC, so Spock Society. And they promote Star Trek and other science fiction TV shows. So I said, well, maybe they know something about extraterrestrials. So I sat down and said, do you know anything about extraterrestrials? And they said, do we ever? Here, come on. And so he talked for about an hour about all the extraterrestrials in the universe that he knew about, or thought he knew about. And at the end of this hour, he looked me in the eye and said, how can you teach a course on extraterrestrials? You don't know anything about extraterrestrials. Have I was a little bit disappointed by that. I said, geez. But it only lasted for about 5 seconds, because I have been trained as an astronomer and astrophysicist, and I know about cosmology. And plus, my dad's a biologist. That's another thing about me. My dad was a high school biology teacher. So I consider myself to know more biology than any cosmologist I know, and more cosmology than any biologist I know. So that's what I do, cosmobiology. It's not a field yet, but I'm trying to turn it into one. So you don't know anything about ETs? And I said, yes, I do. For example, I know that Superman came from the planet Krypton. Now, Superman looks a lot like a human being. And so there's an example of a human being who has evolved on another planet. And as a biologist, you should know that that doesn't occur. As a matter of fact, we do not have any examples of species independently evolving on 2 different continents. If you have a species on one continent, you will never find a species that has evolved independently that is the same species. Nothing that evolved in Australia, for example, could mate with something that evolved in South America. Species do not evolve independently. So the idea of having a human being evolve on Krypton is something that every biologist in this room knows is a crazy idea. Of course, you don't need to be a biologist to know that. And we know that Superman is supposed to be a human being, a Homo sapiens, because he flirts with Lois Lane, and I've been told that they have had children together. Now, this guy is also a human being. Why? Because the definition of a species is, if you take a male and a female, and they mate, and they had an offspring, then those two were the same species. One caveat, that offspring has to be fertile. Now, I think that Mr. Spock is fertile, but I'm not sure. Is anybody a fan of Star Trek? Do you happen to know if he ever gets married or has sex with
I never saw as episode.
You never saw an episode. He's not like Captain Kirk. Okay. All right. Anyway, his father was from Vulcan. His mother was the Homo sapien from Earth. And so let's just say he's a human being. So that's a ridiculous example of two species that evolved on separate planets. Now that's not what happens, as I said, because that does not happen even on the separate continents we have on Earth. Now here's another thing I know, that this is the Earth. This is a picture of the Earth and the Moon. That's how big they are, that's how far apart they are. Now no other picture of the Earth has ever been taken further away. This is a picture of the Earth that Carl Sagan got the NASA team to turn the Voyager spacecraft around and look almost into the sun and see this pale blue dot of the Earth. This is our planet, this is where we live. Now that was a dangerous maneuver, and you can see that there's a diffraction line right through that image because it was looking very close to the sun. And that's why NASA was a little reluctant to do it. But Carl Sagan used some of his influence to get NASA to do that. That's the Earth, that's where we are. I should say that if you have any questions, just call out and I'll try to answer them the best I can. I'm a little bit rude like that too, and I like the interaction, if possible. So, now, another thing I know is that these are stars, and I know that the sun is a star. We have known that the sun is a star for about 500 years or so. And this is a particularly dense star field in our galaxy. And we know that we live in a galaxy of about 100 or 300 billion stars. And we know that we live in a universe that's filled with galaxies. And I'm going to tell you a little bit about our observable universe. One is that there are about 10 to the 11, that's 100 billion galaxies in our observable universe. And each of them has about 100 billion stars. So you multiply those together, you get 10 to the 22. I don't know what number that is, but it's 10 to the 22 stars in the observable universe. Now, I suspect that there are planets around each of those stars, some kind of planets, and that's a lot of places to have possibility for life to get started. But I want to tell you about Fermi's paradox. Fermi was a very famous physicist who died in 1954, Italian physicist, and all physicists know about him. And he was having lunch one day, and he thought of the following. He said, you know what? We probably can make a rocket ship go about 1/10 the speed of light. And so there's a rocket ship. Now, our rocket ships can't do that yet, but that's not out of the question. It's not very. If we really, really wanted to make a rocket ship go that fast, we probably could do that in 10 years or so. Now, we know also that the size of the galaxy is about 100,000 light years across. So that's our galaxy. We live about here, and it's 100,000 light years across. So the question is, how long does it take you to get across the galaxy? Well, if you travel at 1/10 the speed of light, there you do a little algebra, and you get, it takes 1,000,000 years to travel from one side of the galaxy to the other. Now, how long has that galaxy been around? We know that too. The galaxy is 10 billion years old. And so, how many times during the age of the galaxy could a rocket ship traveling at that speed go back and forth? And the answer is 10 to the 10 divided by 10 to the 6, and you get 10 to the 4 voyages across the galaxy. So if there was a civilization that evolved around one of the first stars to form about 10 billion years ago, and they built a spaceship that could travel 1/10 the speed of light, they could have gone back and forth and back and forth and back and forth and back and forth 10,000 times. And on the back of an envelope, Enrico Fermi did this calculation, and then he said, where are they? In other words, if you assume that there are civilizations out there, and they could have evolved around other stars very quickly after a star formed in our galaxy, then they could have gone back and forth 10,000 times. In other words, they should have been able to colonize the galaxy, and we should see remnants of spaceships or on the Earth, for example. But we don't see that. As a matter of fact, when we dig into our own past, we do not find spaceships or rocket-powered lithium dilithium crystals from star outer space. We find are things that look like this. And when we listen out into outer space with our best radio telescopes, we don't hear anything. So we have no evidence for colonization. We have silence from our radio telescopes. And so we're asking the question, where is everybody? Are we alone? That's the evidence we have. Now, some other things about where we are. This is a slide of what happened in the universe. It's very simple. Astronomy turned into biology. At least that's in our homocentric way of looking at things. So we have the Big Bang here 13.8 billion years ago. There were overdensities and underdensities of hydrogen and helium. They produced these big stars, which are blue, and the red stars, which are small. Those red stars have lifetimes of about 100 billion years. The age of the galaxy, the age of the universe is 13.8 billion years. So these red stars, these small ones, have lifetimes that are much, much, much larger than the current age of the universe. So they do not explode. But the big ones, see the big blue ones there? Those stars have lifetimes of 5 million years, 10 million years, not billion, but million. And so 5 million years after they form, they go boom, and then they produce the elements of which you and I, and this table, and the rug, and the air are made. And those elements are carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, the elements that you learned about in high school chemistry. Now, so then these stars blew up, and those black lines represent those elements. And then when you have a third generation star like our sun, it has debris around it, and that debris is filled with this contamination called carbon, nitrogen, oxygen, silicon, iron, etc. That's contamination. Look at the bottom of this slide. The Big Bang did not produce those elements. Those elements were produced by the largest stars that go supernova, and boom, contaminate the molecular clouds of our galaxy, which then subsequently collapse into stars like our sun. Now, on top of then they form Earth, or Earths, or planets around these other stars. Now notice that there's a tree here. Now this tree is something that's not created from physical dead, it's created from ribosomal RNA. Now, in each of your body, in each of the cells of your body, right now, there is messenger RNA that is being read by ribosomes. I just had a cookie, for example, and I'm breathing in oxygen, and I'm respiring, and I'm oxidizing that stuff. And I'm doing it with the help of proteins, and those proteins have been produced by the ribosomes in my cell, just as right now, your body, and each one of your body, and each cell is producing proteins. Now, we use those proteins, we use the sequences of them, particularly the rRNA, to make this tree. So we have a very accurate estimate of the phylogenetic history of ourselves and all the life forms around us. Now, I will show you later on in the lecture a much more detailed version of this. But the bottom line is that here are animals and fungi and plants. Here are chloroplasts. Here are mitochondria. These chloroplasts used to be free-living bacteria called cyanobacteria. They got engulfed into another cell, and so the plants outside, which are green, are the result of this endosymbiotic union. Similarly, in every cell in your body, you have mitochondria. They used to be free-living. They used to be alpha proteobacteria, and they were engulfed, and they enable you to deal with this poisonous gas around you at the 20% level, which is the oxygen. So, we're able to create this tree. We know a lot about the branching. We know a lot about this physics. This is kind of deterministic. As a physicist, physicists, we don't like quirky things. We like to study things that are so universal that we think they will be the same even beyond the observable universe. For example, we have gravity, and we have electrons and protons. And when we look at stars, we can see the absorption spectra of different elements in these stars. So we know that the other stars that are hundreds and hundreds of light years away are made out of the same stuff as our star. So the elements in your body are not just on Earth, and water is not just on Earth, but these elements are the same everywhere in the cosmos. Now, 4.6 billion years ago, this is what the sun used to look like. It was part of a molecular cloud. It was a clump. And 4.5 billion years later, this evolved. And I want to play this movie. I want to turn this into a movie because this is something that's not only funny, but it's also true. This turned into that. This turned into that. It took 4.5 billion years, but that's what happened. And the question is, does that happen elsewhere? Does that type of organization, from this to that, happen around other stars, on other rocky planets? That's the question we want to answer. Now, one thing we should know is this is a kangaroo, and this is made out of CHON, C-H-O-N, carbon, hydrogen, oxygen, nitrogen, and about 1% sulfur and phosphorus. So those are the 6 elements that you need to know about. And when we ask ourselves the question, what are the prerequisites for this transition from a cold, odorless gas to a life form? Do we know enough about this transition so that we can make some guesstimates about whether it does or does not happen elsewhere? As a physicist, we can see stars forming elsewhere, and so we know that other stars form. In the last 10 years, we have also been able to say that planets are also forming around other stars. As a matter of fact, many of us think that every time you see a star up in the sky, it will have some type of planetary system. I think it will also have some type of rocky planets around them. Not only planets like Jupiter and Saturn, which are big balls of hydrogen and helium with a little bit of rock in their cores, but rocky planets like Mars and Venus, the Earth, Mercury, the Moon. These are the rocky planets of our solar system. And you notice that those are the ones that are closest to the sun. It's not an accident that those are closer to the sun because the type of material, rock, is called refractory material. It's not made out of a gas. Hydrogen and helium has been blown away from the inner part of the solar system and leaving only the rock, and that's what we're living on. So, as a matter of fact, if you'd like to know what the universe is made of, here's what the universe is made of: vacuum energy, that's nothing. And here's dark matter, and here's normal matter. The sun is made out of hydrogen and helium, at about 1.5%. I should apologize for some of these numbers because we keep on making progress. This 5% should be 4.4%. This 2% should be 1.6% plus or minus 0.3%. Okay, so we are making progress in getting this the budget of the material in the universe. And then here is what you and I and the tree outside and this wood is made of. And that's hydrogen, carbon, so hydrocarbons, and oxygen. So this is mostly water, right? See that? H2O, it's water. And then nitrogen and 1% other stuff. Any questions about this? This is something that I think every human being on this planet should know what they're made of. I think that's part of a humanist tradition that every university graduate should know that they are about 60 or 70% water, and the rest is carbon and nitrogen and phosphorus, a little bit of pepper, salt, phosphorus, and nitrogen. But in any case, this is not just you. This is also the bacteria in your mouth. This is also the fungus between your toes. These are the dandelions outside, the trees and the grass outside. They are also approximately made out of the same stuff as we are. So these error bars are small, but the components are pretty much the same. Now, this is the composition of the sun, and it is also fairly representative of the entire universe. If you exclude the vacuum energy and the dark matter, and you just concentrate on chemistry and baryons, then this is what you have. This is a logarithmic plot, so for you humanities students who don't know what the logarithmic plot hots mean. That means when you're high here, you're really, really high. So, although, for example, here it looks like you're only about 30% more, well now you're 1,000 times more abundant here. See, hydrogen and helium is really, the universe is made out of this stuff, and everything else is kind of almost meaningless. But it's not, because C, N, and O, and H are the most abundant stuff in the universe, and that's what you're made out of. It's a little like being made out of your bread, and you say, what am I made of? Well, you look around and you see flour and water, and you say, well, that's what I'm made of, it's no surprise. Now, in 1954, Stanley Miller and his advisor, Urey, devised an experiment, and they wanted to know, hey, maybe we can make some life in the laboratory. And so what they did was they took some water, and they had some electrodes here, and they filled this vessel with what are called reduced gases. And this H2O, anything with an H is reduced gas. So this is ammonia and hydrogen, and then they sparked it, and then they ran this through, they cooled it down, and they heated it, and they just essentially went in a circle. And after a few days, they checked what was here. And what they found were amino acids. So here was a simple gas mixture, add some energy, and then run it in a cycle, and you produce amino acids. And amino acids are what proteins are made of. If you take amino acid, hook it to another amino acid, hook another, like a train, you have a monomer hooked in to make a polymer, and that's what your cheek is made of, that's what your brain is made of, that you're using to think right now, trying to follow this talk. That's what your eyeballs are made of, and your feet, and etc. Everything. Now, everybody thought that was a lot of progress, but then we were surprised when a carbonaceous chondrite, a large carbonaceous chondrite, fell from the sky, and in Victoria, in 1969, Victoria is a part of the province, territory of Australia. And here's a picture of it. It's a black thing. It falls from the sky. These things are called carbonaceous chondrites. And when we analyzed this, we found not just the 20 amino acids in our bodies, there were 80 amino acids, 80 different types of amino acids. Now, 8 of those 80 were a member of the 20 that all life on Earth uses. These 8 were the most abundant ones that we use. Essentially, that amino acids, the monomers, the ingredients for life, were falling from the sky. And we have very good reason to believe that these carbonaceous chondrites were much, much more abundant and fell much more, well, there were a lot more of them earlier on in the history of the Earth, in the first 500 million years, the first 500 million years after the origin of the Earth. The bombardment rate was much, much higher. And so there was a lot of this stuff falling, so a lot of amino acids were falling literally from the sky. Now, I think that means that on other rocky planets, they too are being bombarded by these amino acids, which were formed in the molecular clouds out of which the star and the planets formed. So notice I'm making a jump here. I'm trying to tell you our understanding of the Earth and the Sun, and some of that understanding is easily extrapolatable to other stars and the other planets around them. Other types of information is not so easy. So it's not hard to believe that the other stars are made out of hydrogen and helium. It's not hard to believe that you will have rocky planets around other stars. But let's see. One other point. This is age of a star. Here's today. Here's 1 billion years ago, 2 billion years ago, 3 billion years ago, etc. Here's the relative amount of surface area. It says, how old are the surfaces of the rocky planets? Well, if you look at the moon, most of the moon is about 4 billion years old. And only very little of it is very recent. If you walk around the Earth, however, you will find surface area that's a few 100 million years old. Very, very little of the Earth is 1 billion, 2 billion, 3 billion years old. And we can see that very easily because we look at the moon and Mercury and Mars, we see craters all over the place. The Earth used to be cratered like that as well, but we have the advantage of having water and rain and erosion and plate tectonics, and all those processes just clean up the place and make all those craters go away. But these do not have weather. They do not have wind. Well, Mars has a little bit of wind, but they do not have water. They do not have a hydrological cycle. And so they are very good addicts. They're very good reminders of what the Earth went through. Now, one of the things we do in astrobiology is keep track of our continually increasing knowledge of the number of exoplanets. Exoplanets are planets that have been discovered around other stars, not around our sun, but around other stars. And when everybody in this room was born, we did not know of any exoplanets. The first exoplanet was in 1992 or 1995. And so this is a very recent science. And what you're looking at here is the period, the orbital period of a planet, and then the mass of the planet. And you can see here, you and I are now living on the Earth. And there's this period, it was 365-day orbital period around the sun. And it has a mass of, about 1/300th of a Jupiter mass. This is the units here. So Jupiter is right there. Here's Saturn, here's Mars, Earth, Venus, Mercury. So this is what our solar system looks like on this plot. We would like to know, we're desperate to know, are the other planetary systems like ours? Or are they different? We've found lots of planets, but are the planetary systems like ours? Do other planetary systems have rocky planets here that are low mass, and then high mass planets further out? And you may have heard in the news that, the planets that we're discovering are not like ours. And that is one of the most misleading things that you will read in the newspapers. It's misleading because we cannot find yet planetary systems like ours. Notice that Jupiter, the most easily observable part of our solar system, is just at the border of being detected. Here are the things we can detect easily. Here are the things we are detecting. And here are things that are much harder, even impossible to detect. As time goes by, then these lines here move to the right. I should say that these are a little bit different because those are the result of direct imaging. These are hot planets that are hot because they've just formed and they're very far away from their host stars and they're directly imaged. They're not found by the technique of radial velocities or Dopplers. The point here is that we have not been able to detect planetary systems like our own, and so the fact that the systems that we have detected are not like our own is no surprise. Last month, the Kepler satellite, which is staring in a particular direction near the constellation Cygnus, and it just stares and stares and stares, and it looks for dips in the light that change. The light gets darker and lighter and darker and lighter, and that's what happens when a planet passes in front of the star. And the photometric accuracy, how accurately it can measure this dipping of the light, is better than any other satellite ever made. And they recently found 1,200 planets. What you're looking at here is about 400 planets, but let me show you, I recently have a student who plotted these new planets up, and it looks like that. So we have all of these were announced last month. Notice that we're starting to get closer to where the Earth is. We're starting to get planets that are of Earth mass and a little bit lower, but they're in closer orbits. That's again because of the selection technique associated with the type of satellite it is. We can detect ones here, but it's very hard to detect things out here. So again, we're getting closer to detecting real Earth-like planets, but we're not there yet. Now, all right, so it's not too hard to say, there are probably terrestrial planets around every single star you can see at night. And that's not too much of an extrapolation. I think it's a reasonable hypothesis that we will be able to check that in the next 2 or 3 years. Now, but what about life? Is life a convergent feature of molecular evolution? We think life got started by some process of molecular evolution on this planet about 4 billion years ago. As a matter of fact, the earliest evidence we have for life on this planet is 3.85 billion. So life got started sometime before then. To put that in perspective, here's today, and here's the origin of the Earth, 4.5 billion years. Life got started right there, as far as we know. Maybe a little bit earlier, we're not sure. But the oldest evidence is 3.85. Maybe it's 4, maybe it's 4.2, we're not sure. But during that first 500 million years, we know that the Earth was bombarded just like the moon was bombarded. And so an incredible amount of bombardment going on. Maybe it is the case that as soon as the bombardment rate went down, then life could get started. Maybe life got started, and then a giant thing hit the Earth, sterilized it, and life got started again. Boom, it got sterilized again, life got started again. Maybe it was sterilized multiple times. Finally, the bombardment rate slowed down enough so that when life got started, it could maintain itself. It didn't get sterilized. And I've written an article about that with Paul Davies. So is life a convergent feature of molecular evolution? So, I mean, one way to approach this is there anything special about the Earth? Is the Earth made out of something unique? Is there some type of chemistry about the Earth that makes it different from what we think the chemistry of other Earth-like planets is? And the answer is no. We have not found anything special about the Earth. The Earth is made out of the same chemistry that we think the planets around other stars are made from. Now I want to talk about another topic that many of us are interested in, and that is human-like intelligence a convergent feature of evolution? When I asked the question at the beginning of this talk, are we alone? Probably about half of you interpreted the word we to mean we Homo sapiens, we the human-like intelligences of this planet. The other half, maybe the more sophisticated half of you, said, we the life forms. Are we the life forms of Earth alone in the universe? And if you said, or you could say, are we Homo sapiens alone in the universe? Now, if you thought, are we Homo sapiens alone in the universe, you were really being bad, because you know that Homo sapiens are not alone on Earth. So we cannot be alone in the universe, right? If you're not even alone in your neighborhood, then you can't be alone in the entire Earth. If you're not alone on Earth, then you're not alone in the universe. So Homo sapiens are definitely not alone. But how about human-like intelligence? In some sense, we define human-like intelligence so it is species-specific. Some people do. Other people say, oh, we're not quite sure what intelligence is. But other people define intelligence such that it is human-like. Only we have it. And biologists tend, if you ask a biologist, is human-like intelligence a convergent feature of evolution? Biologists say, no, I don't think so. Matter of fact, do we have any biologists in the room? Is human-like intelligence a convergent feature of evolution? What's that? Well, I'll tell you how you can answer. Matter of fact, you can listen to me. How about, do we have another biologist who wants to stick their neck out further? Is there only one biologist? That's what we're going to do. Well, how about an Indian elephant? Is Indian elephant a convergent feature of evolution? Do other species try to become Indian elephants? Physicists who think that brains are very important, and Hollywood who think that people who look like people are very important, they think the answer is yes. And as you can see, that this is a physicist in a Hollywood's version of an alien. Notice that the important part of the physicist's body has been blown up, and he's very smart. There's Captain Kirk, somebody who thinks that violence is more important than brains. And anyway, there's this disagreement among these two communities, and you should be aware of that. And I want to tell you a story about the Planet of the Apes. Has anyone seen this movie? Raise your hand. Okay. Oh, good. Now, Planet of the Apes is a story about this guy, Charlton Heston. He is in a spaceship with a bunch of other scientists. These are biologists and physicists. And they're in suspended animation, and for some reason their ship goes crazy, and they crash land on a planet. And they get out of this planet, they get out of the spaceship, and they walk around and they have all these monitors, like, oh, the atmosphere, oh, it's breathable. And now what's crazy about this film is that although these guys are scientists, they have landed on a planet in which the day is 24 hours long, in which the oxygen content is 20% and the nitrogen content is 80%. There is corn growing in the field, there are horses there, there are apes using cameras, riding around on horses, and there are also human beings. And during the whole movie, these scientists don't know that they've landed on Earth. They think that all these things must be, they were just clueless. And they only knew that they landed on Earth when they saw the Statue of Liberty half buried in the sand. And Charlton Heston got down on his knees and said, "My God, what have we done?" And I was saying, "Charlton, you guys are so stupid. What? I mean, if you measure the length of the day on the planet, and it's exactly the length of the day on the Earth, you are on the same planet." He didn't know they had crash landed on the Earth. So the science of this movie is already a little dubious. Now what happens is Charlton Heston gets captured, and on this planet we have the chimpanzees, which are, I guess the normal people, and then the religious people are the orangutans, and then the goons, the thugs, the military people are the gorillas. So that's the planet of the apes. Now, the idea, let me show you. So here's Charlton Heston in a cave here. You can see they have Victorian technology here. He's got a rifle here, for example. Look at the key there, right? And it's got a big wooden keychain. Look at the I guess he can club people with that. Now, so there he is saying, "My God." He's also got a woman here who's got a half naked there. Anyway, so the Planet of the Apes hypothesis is, this is what many of us grew up with. And I accuse you of having this in your head. I accused you of this yesterday in our discussion. This is what most people on the planet Earth have in their head, secretly instilled there from childhood. And that is, we humans occupy a niche called intelligence, towards which all, or at least some species, evolve. And down here are apes, dogs, sheep, and vertebrates with half a brain. And they would, if we ever kill ourselves, they will evolve into us, into this niche. And down here, bacteria, worms, fungi, and stupid things. So we've created this pyramid of intelligence with us at the top. And any time in the history of science when we people put ourselves at the top of something, we're doomed to fail. Because science keeps on telling us, and I don't think it's an accident. I mean, if you think you're the greatest thing on Earth, you're just going to fall. There's only one way, and that's down. Of course, if you think you're the worst thing, there's only one way, it's up. But so it's all a function of your expectations. But look at this plot here. Now, this was made in 1959, and I call it the Schwarzeneggerization of life. Why? Because you can see that the main purpose is to become Arnold Schwarzenegger. and some type of Aryan bodybuilding male who's tall. And that's what this primordial cell knew it wanted to evolve into. Now, you're always laughing. I hope you laugh at that and continue to laugh at that, because it really is sick. But this is something that was in 1959. This is not some pre-World War II, Aryan philosophy. This is a scientist, a legitimate scientist in 1959 writing this, trying to understand macroevolution, trying to understand macro patterns in the evolution of life. Well, you can see that not only are we supposed to become Schwarzenegger, they've taken, look, you see any plants? See any plants? Oh yeah, the plants are over here. Plants, okay, plants over here. That's what's literally called being marginalized. Now, do you see any fungi? There are no fungi here. So fungi just been ignored, okay? So this is the type of understanding that I hope we can get beyond. As a matter of fact, I want to show you the modern version of this. Look at this, that's a Schwarzeneggerization of life. And the modern version of this is something I want you to take much more seriously. And this is based on that ribosomal RNA I was talking to you about. So, Homo is right here. These are animals here, as represented by Homo sapiens. Coprianus is a fungus, and Zea is corn, or maize. And And you notice that this is a tiny, tiny branch of the tree of life. This is a tree of the diversity of life, but I should say out of the corner of my mouth. Matter of fact, let me ask the biologist there. Viruses, they're not on this tree. Are viruses alive? Say it? Still under debate. Yes, it is. It's still under debate. Do you think the debate will ever end? Okay. All right, so what I think, and I think it's an interesting idea, and that notice that the things at the root of the tree of life are hyperthermophilic bacteria. These are things that like to live in water above 90 degrees. Now, do you know how the temperature of the bathtub was yesterday, or the shower that you took this morning or yesterday? Do you know what the temperature of that hot water was? Anybody? About 40 degrees, right. Notice that here we are here, and all of these creatures in green are eukaryotes, and they like to be beneath 60 degrees. Because if we get into 60-degree water, our proteins start to denature, like an egg on a frying pan. Your proteins denature like that, no good, you die. And so all of these things cannot live above 60 degrees. That's an upper temperature limit. But these guys, in the red, they can live up to 90 degrees, and the current limit for the highest temperature of life is 122 degrees. So this is I should say that any one of these branches, there are hundreds and hundreds, well, for example, you know all about the animals. There are thousands and thousands of species of animals, and so this particular branch could be turned into thousands and thousands of branches. This is just the big picture, which we've ignored, not many of the details. Now, what about the Drake equation? What about in alien life elsewhere? I sat on a plane with Frank. He's a radio astronomer from Cornell University, and now he's at the SETI Institute in California. And I said, Frank, why do you think there are intelligent aliens who have built radio telescopes? We were on our way to a conference, and I just happened to sit next to him. And I said, what do you think is the strongest evidence for the idea that human-like intelligence is a convergent feature of evolution? And he told me, read Harry Jerrison. I'd never heard of Harry Jerrison. So I read Harry Jerrison. And Harry Jerrison has this plot in the article he was talking to about. So here's today, here's 100 million years ago, here's 200 million years ago, and this is relative brain size. So what Harry Jerrison does is he gets fossils and he measures the size of the body and the size of the brain case of fossil animals. And then he plots them as a function of time. And he says, okay, here's humans, and here's Australopithecine and prosimians, and then insectivores and archaic mammals and lower vertebrates. So here we have an example of something that looks like, wow, the relative brain size is increasing as it comes to human beings. And many of you might take that, like Frank Drake did, as evidence that human-like intelligence is a convergent feature of evolution. But I did a lot of data analysis into doing my PhD, and I want to tell you the main thing wrong with that conclusion. It's a subtle thing. It's not that subtle. But imagine that you are an elephant. And instead of IQ, I should say that this is EQ, encephalization quotient. Encephalization quotient, the ratio brain size to body size. So that's called encephalization quotient. It was invented by Harry Jerrison. But imagine if you're an elephant, and you have many features, and you look around and say, I've got really thick skin, I'm pretty special. And then you see a rhinoceros and say, I've got thick skin too, it's a pachyderm like me, maybe I'm not so special.